Statistics and probability go hand in hand. In statistics, we're interested in populations and finding out things about populations of people and populations of automobile tires, which is the average mileage that you get from a set of automobile tires that you might buy. We might be interested in the population of automobiles and the average miles per gallon, but we can never measure every element in a population. So we draw samples. We compute a statistic from that sample. That statistic could be an average, it could be a standard deviation, it could be a median, or it could be a mode. And then we hope to generalize what we learned from the sample to the population. But we know that there's going to be some uncertainty in making that generalization. We didn't measure every element of the population. You didn't measure every tire. You didn't sample every student. We didn't take a poll of every voter in the country. We only took a poll from a sample, let's say, of 1,000 voters. And when we say that, well, the proportion of people in the country who favor or are opposed to a particular policy is 60% or 40% or 30%, we have an element of uncertainty in making that statement because we know we didn't sample everyone. So you have to have some basic understanding of probability in order to have a real grasp of statistics and a lot of the analyses that we do with statistics, and that's the purpose of Chapter 6. I won't really have that much to say about the different slides that you'll see in Chapter 6. I'll only comment on those particularly those where they are figures and there are no words or text that goes along with the slide. There's a video that I prepared that's under this unit in Canvas, which gives an explanation of how to use the normal curve table. And so you might want to check that out. That provides a pretty decent explanation of what's on this PowerPoint. So let's advance the slides, pause them, and when you advance to the narrative, there may or may not be a narrative. If you hear nothing, then just go to the next slide. But when there is just a picture or a graph or something, I'll comment on that. I would say the only thing that I would comment on about this slide is that probabilities doesn't only apply to drawing specific samples or apply to statistics that we get from specific samples. Probability can be applied, as we know, in gambling to one throw of a die or two throw of a die or drawing a card or flipping a coin. And we want to know what's the probability of getting ahead when you toss a coin. There are two possibilities. When you toss a coin, there are two things that could happen. You get a head or a tail. The probability of getting ahead would be 1 over 2. When you toss one die, there are 6 things that could happen, that could come up. If you're interested in what's the likelihood of getting a 6, well, that would be 1. The probability would be 1 in 6. There are 4 kings in a deck of cards. What's the probability of randomly picking a king from a deck? Well, there are 52 cards. There are 4 kings. The probability would be 4 over 52. So in statistics, then, we are drawing samples because we can't often get access to every element or member of the population. As I said, whether the population is people, whether the population is automobile tires, whether the population are iPhones, and we want to find something about that population. Since we can't get access to the entire population, we draw a sample. We compute a statistic from that sample. That sample should be a probability sample. That sample, and by a probability sample, we would mean a sample where every person in the population could have been in the sample. But when we get that probability sample and we compute a statistic, and we want to generalize back to the population, which is the area of inferential statistics, we know there is a degree of uncertainty in making that generalization. So when we, as you'll see in chapters that follow, if we take a sample, compute a mean, and then try to generalize that mean to the parameter of the population. We generalize with a certain element of uncertainty, and we couch that uncertainty in terms of probability statements. So probability is how we determine the likelihood of statistics from specific samples. The important thing about this slide is that when we're looking at a graph, when we're looking at a histogram, when we're looking at a frequency distribution, probability is determined by a fraction or proportion of that distribution, and it's usually an area under the normal curve. In order to determine the probability of a specific statistic, let's say like an average, we have to change that statistic to a z-score, which we learned how to do in the previous chapter. And then we look at the graph to determine what's the likelihood of a score equal to or greater than a particular z-score, what's the likelihood of a score equal to or less than a particular z-score, and we have a table that tells us the exact probability. We don't have to compute the probability by hand. We have a table that tells us what that probability is. How to use a unit normal curve table is explained on the video that goes along with this unit. So all of the details of this slide are explained in that video. This is the table of the normal curve that your books provide. We have provided a longer table, one that has every z-score and its probability is described in that table, and again I've demonstrated how to use that table on that video, and so I won't really be having any more comments about this page. In order to determine the probability of a particular value of a particular score, you have to change that score to a z-score. You learned how to do that in Chapter 5. And then you look up that z-score in the table, and you find out, what's the probability of a score greater than that score, or what's the probability of a score less than that score, and you know whether to look in the body or the tail depending on whether you're dealing with a plus z-score or a minus z-score. We've talked earlier, I think it was Chapter 2, where we talked about percentile ranks. When you're looking at a normal curve table, the percentile is the proportion of people to your left. So let's go back a few slides to this one right here. And let's say let's look at the histogram on the top, where let's say our z-score is plus 0.25, and we're interested in the percentile rank for that z-score. We're interested then in what proportion of the scores are below that score, are to its left. So we would look at our z-score table. You see a z-score of 0.25. We're interested in the proportion in the body, and so the percentile rank is almost the 60th percentile, 0.5987. So a proportion and a percentile are treated the same. If we're interested, for example, in what is the percentile of someone who gets a z-score of plus 34, let's say minus 0.34, then we would be to the left of the mean. We would be interested in the tail, and the percentile rank of someone who has a z-score of negative 0.34 would be about 37th percentile, 0.3669. When we look at this chart, we can determine the percentile rank for a z-score of 1. We can determine the percentile rank for a z-score of 1.5. It's the proportion of people to its left. We can determine the percentile rank for a z-score of minus 0.5. In the histograms in the middle, we have a z-score. But what is a z-score, for example? That's at the 90th percentile. I show how to use that in the video. You would look at your table, you would find 90% in the body and find out what z-score cuts off 90% from 10%. So you can use your z-score table for not only determining the percentile for a given z-score, once you have that z-score, but you can also find the z-score that's located for a z-score that represents a particular percentile rank. If you're asked, well, what is the z-score that's at the 60th percentile, you can determine that from the table. So we're always interested in statistics about what's the probability of getting a particular value from a particular sample, and probability helps us do that. As you'll see when we engage in hypothesis testing, often a certain assumption is made about a population value. From that population, you draw a sample, and you might get a different value from what it's assumed the population parameter is. And then the question is, well, what's the likelihood of your getting a particular statistical value from a sample when people say that the population is parameter is of a particular value? So let's say that you're in a school and someone says, well, the average IQ of students in this school is 100, and you take a random sample and you take a random sample of 100 students and you compute it to be 98. Your question would be, well, if the average IQ of students in the school is 100 and I take a sample and get 98, what's the likelihood of that happening? You would phrase that likelihood in terms of probability, and that's one of the reasons we go into probability. We're always trying to determine what's the likelihood of particular values of samples given what we think we know about a population. Often we have information about a population. In this case, we have a normal population, and the population parameter is 400. Let's say that's an SAT score of 400, and the standard deviation is 20. And we want to see if we can improve students' ability to, or student scores on the SAT. Let's say it's the SAT math, and in the population, most people score 400. U equals 400, that's the population parameter, and the standard deviation is 20. So you take a random sample of students from that population, and you put them through some special training program in how to take the SAT. They take the SAT again, so we have now our treated sample, and let's say that the average of that treated sample is 500, 100 points higher. And if the question then would be, well, is that difference between 500 and 400 simply due to sampling, or is it due to the fact that the treatment was really effective? What the graph on what the histogram on the right is trying to show is that when we draw samples from a population, we get certain values that are very likely and certain values that are not. If the mean of the population is 400, and we take a sample and we compute the average to be 420, which would be one standard deviation above the mean, somewhere around here, that is not that unlikely. That could happen simply due to sampling error. On the other hand, if you were to take a sample from this population and compute the average to be 600, which would be many standard deviations above the mean, then we would say that's very unlikely. That's a very unlikely occurrence, and maybe, in fact, we made some wrong assumptions about that population. So whenever we take a sample from a population, we have values, we compute statistics from that population, which are likely given the assumptions that we've made about the population, and sometimes we compute a statistic from a population and we're getting a value which is very unlikely. And as you'll learn in chapters 8 and 9, how you determine what is the z-score for a particular sample, and whether that z-score that you get for a particular sample, for a particular statistic, is very unlikely, given what you know about the population, or very unlikely. This is all rather abstract now, but it will become clearer. But probability is the way that we determine whether samples are likely to come from a particular population or not likely to come from a particular population.